Hello everyone and welcome to our talk Spectra, breaking separation between wireless chips. So this is a topic I've been working on together with Francesco, and Francesco is an expert for Wi-Fi and other wireless technologies, while I have been working on mainly with Bluetooth. And in this talk, we bring our abilities together and break the separation between different wireless chips. Let me first start with a motivation. So a while ago, I found a partial RCE within a Broadcom Bluetooth chip, and then later on, a student of mine, Jan, built Frankenstein, and with this, he actually found even more full RCEs within Broadcom Bluetooth chips. And now this is a cool thing, and I said like, yay, let me take my unicorn and tour the world and tell everyone like, yay, we have Bluetooth RCE and Bluetooth is insecure and so on. And then people said like, yeah, but you know, Bluetooth, it's like 22 years of expensive iterative development and it's indistinguishable from Magic anyway. And yeah, we know it's insecure. We live with that. And actually, because of this, we try to sandbox Bluetooth as much as possible. You know, it's actually just connected with UART. It's not using PCI Express. And also, can you pop calc with a Bluetooth RCE? So yeah, people said like, you know, you have the Bluetooth RCE, but what would be really cool is if you had a Wi-Fi RCE. And now one option would be, of course, to port the fuzzer and everything that we have to Wi-Fi and do the same thing again. But actually, Wi-Fi RCEs have been found in the past with different technologies and so on. So it would not have been something new and also a bit boring. And then I thought like, yeah, maybe there's another thing that we can do, which is actually breaking the chip separation. So saying I have a Bluetooth RCE, can I attack Wi-Fi or even LTE instead of going all the way up to the operating system? And so I called Francesco and said like, yeah, you know, let's build something called speculative transmission. And so this was the initial attack name or idea, because Wi-Fi, Bluetooth, and LTE, they all share frequencies in the 2.4 gigahertz spectrum. Even if they don't share the same frequency, they still have harmonics that interfere and so on. And everything like in a modern smartphone is really built to this form factor. And because of this, you somehow need to arbitrate channel access. Well, and this is actually a performance optimization. So because they share the spectrum during the transmission, they somehow need to tell each other, I'm now using this and that frequency, I'm now sending a packet, because they cannot do it at once without causing interference. And this is also called a coexistence mechanism. And the idea was to use this for a side channel, for example, to speculatively transmit a packet in Wi-Fi or Bluetooth and then tell what the other one is doing. It got a bit broader in the end, so I would more call it like a spectrum transmission by now, but yeah, whatever. The attack model overall is that an attacker has code execution, which we have in Bluetooth in this case with the technologies that we use to find vulnerabilities. And now then with this prerequisite somehow attack the other wireless cores. And while this is a pretty strong prerequisite, it also is a strong attack primitive overall, because these chips have hardwired connections, and these connections can be used without passing any checks by the operating system. So to show you this, here is an example for a modern iPhone. There you have the Bluetooth chip running and the Wi-Fi chip running, and they run on separate ARM cores. So one is a Cortex M3 or M4, and the other one is a Cortex R4, for example. And they have this interface here, the serial enhanced coexistence interface, which is a hardwired connection between the two. And then between this Bluetooth Wi-Fi combo chip, there's also another connection to the LTE chip, which is MWS, Mobile Wireless Standards. And now we get some new attack paths on this. So for example, an attacker could start here at the Bluetooth core and then escalate from the RCE that he has there, like to the Wi-Fi core, and then go all the way up and have the traditional attack that we know, like going into the operating system. Or we could also have apps that now know that timings between the Bluetooth and Wi-Fi frames are somehow hardwired and not random. And maybe they can also use this hardwired timing to like escalate something here in between and infer some information. The impact can be varying a lot depending on the chip and the implementation of coexistence. So the obvious one is denial of service, so that you say, I have to transmit, and block the others. Or some information disclosure by this meta information about the packets that you're going to send, which could also be in the timing of the packets and so on. And maybe if the implementation is really screwed up, an attacker might gain code execution. Now, the attack name is a bit, let's say, complicated because it's hard to find on the internet, as Spectra is already a word. And so you might also stick to this alternate name, which is the queer ghost attack, whatever, go for whatever name you prefer. And now let's try to exploit all of this. So there is the Broadcom coexistence interface, and actually the same coexistence interface is used by Cypress because they acquired parts of Broadcom in 2016, and they use the same code, the same hardware. So I might use those terms similarly. We really like Broadcom because they don't do any firmware check. That means they don't have secure boot or something. You can just modify the firmware. I mean, just modify, it's still a thing because, well, the hardware itself, it's easy to get, but then the firmware, you need to load it into IDA, you don't have symbols and so on. So it's still a complicated thing, but you don't have to bypass other security mechanisms. And well, these chips are used in so many devices, like really all iPhones, all MacBooks, iMacs, and also the older Apple Watches. The newest Apple Watch has a different chip. The Samsung Galaxy S series, Note series, and so on in Europe. Also the older Google Nexus phones or Raspberry Pis, a lot of IoT devices. So there are many devices to pick from that can now be used to test certain attacks for prototyping. And now the coexistence idea is that we escalate within the chip components. And here you can see a data sheet of a chip that's used in the Google Nexus 5. The reason why I took such an old data sheet is that the newer data sheets are often not available or not as extensive because they are still like closed under NDA and so on. But Cypress actually published a lot of data sheets of the older chips, and they are now openly available, and you can look a few things up there. So what you can see is in this detailed view, like there's an ARM Cortex-M3, there's the other ARM Cortex-R4, and in between there's a lot going on, which we exploit in the following. And then there's also this shared antenna, and it's shared for 2.4 and 5 gigahertz, has a duplexer, other complicated stuff going on. Yeah, so this is our attack surface. If you look for data sheets that somehow mention the product, what you can see here is one data sheet about coexistence, and it's by Cypress, and they state collaborative coexistence between WLAN and Bluetooth is implemented according to IEEE 802.15.2 packet arbitration. That's a scheme that defines different traffic priorities. So Wi-Fi acknowledgement has a high priority, or SCO, which is used for speech, and Bluetooth has a high priority. And that's an old one. So many chips use it. It's not a thing that Cypress first thought of. But then Cypress continues with, and through Cypress Enhanced Coexistence Interface, ECI. ECI augments PTA by signaling by enabling exchange of additional information required for implementing more advanced collaborative coexistence methods. As a result, overall quality for simultaneous voice, video, and data transmission on an embedded system is achieved. And this is an important point because you cannot simply disable coexistence as to ensure more security. So if you disable coexistence, you are no longer able to stream a video over Wi-Fi and listen to it with your Bluetooth headset. So each of them gets stuck. First the stream stops, and then the Bluetooth sound stops, and so on. So you cannot just disable coexistence. And now let's look into the serial enhanced coexistence interface. It's sometimes with the S for the serial, sometimes without. And then there's also the GCI, which probably means global coexistence interface or generic coexistence interface and many other terms, but they are like used in the same way. So they all mean the same thing. So the serial enhanced coexistence interface, that's used between the Bluetooth and the Wi-Fi chip. And now when we want to exclude any side effects, for example, by shared antennas, we really use those two separate boards, connect them with the serial interface. And the nice thing now is that we don't have any side effects and we can still observe everything that's going on this interface. So we don't need this for the attacks later on, but initially to understand what is going on in the enhanced coexistence interface, it really helps to look into it with a logic analyzer. And if you look now into it in detail, what you can see is, first of all, here the first example has a Bluetooth music stream, and you can see it's sending a lot of data, and it's sending this data with 3 megabaud, which is the same rate that it's using to send data of the actual music stream to the host. So this is a very high data rate. And at the same data rate, Wi-Fi, when you, for example, like scan for Wi-Fi, indicates I'm starting a scan, then there are the scan results that are reported, and then later on the end of the scan. And in the same way, if you zoom in now, you can see that there's data. So you have these bytes, these additional bytes that are sent here and there. So there's something encoded. The last example is a different example. So in this one, I connected this tiny Bluetooth keyboard. And then you can see that there's a regular pattern every 30 milliseconds of sending data. The first attack doesn't even need all this knowledge here, but what it does is it reconfigures this interface. So there are configuration registers, and initially I tried to find everything out, like about each and every register and reverse engineer all the functions. But then Francesco said, like, yeah, you know, just if you don't understand it, first write garbage and see what happens. So I wrote garbage and saw what happened. And well, there is a register, it's called GCI chip control, and it's at the GCI offset 200. It might also be at 400 or 600. It depends on a bit on the chip. And if you write just FF to it, that's it. Then it crashes Wi-Fi. And in this setup with the logic analyzer, we can even see a voltage drop on the SEC-E line. And sometimes to recover Wi-Fi, you need to reboot a device multiple times, not just once. It's a bit strange, at least what I observed. And well, it causes a kernel panic quite often because Wi-Fi behaves so strange that it starts like spamming PCI Express. And like if the device is not rebooting, just the chip is crashing, then the chip crash log still contains a lot of invalid characters and stuff. So it really screws stuff up. Here's a demo of it. It's a bit accelerated because it actually takes a minute. On the left-hand side, you can see that I write to the register at offset 400. And at the right-hand side, you can see how Wi-Fi stops working immediately. So the ping stops, and then a bit later it reboots. And this is on an up-to-date macOS Catalina with a chip that was in the 2019-2020 models. And you can see that many devices are affected of this. So we reported this like a year ago, and it's still unfixed in most devices or most drivers. So I don't even know if it's like fixable on all of them. And yeah, I mean, it's just denial of service, but it's a very nice attack and very easy to test. And the only thing that they fixed is like that now you can no longer write over HCI to this register, but probably remote code execution would still be possible to write to those registers. And because this was a very promising start with all this coexistence stuff, Francesco started to look a bit more onto the Wi-Fi side. So how the D11 core is actually parsing all of this. So with this, I'm handing over to Francesco.
Thanks, Giska, for introducing this part of the talk. Let's start describing the Wi-Fi chipset developed by Broadcom. We see here it evolved in the last 2 decades from a soft Mac to a full Mac implementation. Operations previously performed on the Linux host at the top are offloaded today by an intermediate ARM core. Interestingly, real-time operations are still managed by the same low-level piece of hardware that did not change much in 17 years. No matter it is an 11B card from 2003 or a state-of-the-art 11AX chipset, time-critical operations are managed by the same D11 microcontroller that coordinates all these small blocks, like phi, radio frequency, and DMA. While they claim they switched to full MAC to handle high-throughput features more efficiently, this switch also allowed the manufacturer to better hide driver internals inside the ARM binary code. Let's have a closer look to the low level. Here the D11 microcontroller runs a microcode that is a short piece of software made of 8-byte instructions dedicated to manipulating bits and testing hardware conditions. This is some code from the main loop that checks if the phi started receiving a preamble, useful for analyzing a packet while being received, or if the current reception is terminated, for deciding whether or not to push the frame to the upper layers. This one is extracted from the code that schedules the transmission of an acknowledgement. We see the preparation of the reply frame that starts with D4 as usual. The toolchain for the U-code was created by Michael Buech in 2007, and we incorporated it inside our Nexon project, and we periodically update it by adding instructions when a chipset is introduced if it comes with new specialized instructions. As spotting the U-code in the ARM binary blob is easy, we can modify it adding customized parts, as we will see later. The D11 CPU coordinates several blocks. First of all, it controls the transmission and reception engines, it manages channel access by scheduling transmissions, and decides which received frames should be pushed to the ARM core. It can configure the phi and the radio, and it does so by running the U-code that is loaded to U-code memory by the ARM firmware at every initialization. D11 has access to limited memory called shared memory, up to 8 kilobytes, where it keeps its configuration and its state variables. D11 can also access indirectly the ARM memory, where packets ready for transmission are queued, so that it decides which packets can be transmitted or aggregated. D11 is equipped with several general-purpose timers that can be used in modern platforms for measuring time of flight, and with many different interfaces for talking to other parts of the chipset, like the SECI interface. During the years, it turned out to be a pretty flexible architecture. We demonstrated frequency hopping, time division multiplexing, LTE coexistence, and so on and so forth. In general, we used it as a research platform for anticipating features that were lately added by the manufacturer on its own. Let's now talk about the D11 coexistence interface. There are quite a number of registers dedicated to this interface. There is a 64-bit buffer that U-code polls every 1.25 milliseconds, that is the minimum Bluetooth connection interval, for checking whether new messages came from Bluetooth. Such messages include timing indications from Bluetooth that tells to Wi-Fi, "Hey, I'm doing something for this amount of time," and they also include the type of event which we used for our attacks. There are countdown timers where U-code copies the timing received from Bluetooth for deferring Wi-Fi operations. And there is a Bluetooth transmission control register in red that is used by Wi-Fi for telling Bluetooth, "Hey, stop, I take control of the channel, wait until I grant you access again." We also use this register for our attacks. According to our analysis, 12% of the U-code is dedicated to coexistence, and we refer here to the 43909B0 chipset by Cypress. It's amazing, because U-code is doing so many other things with much less code, like packet aggregation. Probably coexistence takes a lot of room because of its complexity. With the help of an external FPGA, we measured the jitter of the Wi-Fi to Bluetooth SECI line. We modified the U-code in a couple of boards, and we programmed them to transmit SECI messages when receiving the same beacons. Jitter turned out to be Gaussian with a 200 nanosecond deviation, which makes it perfect for Bluetooth coexistence. So what about grant-reject scheme? For studying the SECI protocol, we focused at first on the grant-reject counters that are kept by the Bluetooth firmware and that we can collect by using vendor-specific HCI commands. Every time the Bluetooth has something to transmit, it checks the last grant indication received from the Wi-Fi, and if access is granted, then Bluetooth transmits and increases the grant counter. Otherwise, it increases the reject counter. In this scenario, we are watching a movie that we download over Wi-Fi, listening audio over a Bluetooth headset. At the beginning, we see both grant and reject counters are increasing almost linearly. When we pause the video, the two counters freeze. This is expected because even if Wi-Fi keeps downloading the movie, Bluetooth is no more transmitting sound to the headset. When we restart playing the video, counters restart increasing. When the video download is interrupted by disconnecting from Wi-Fi, we have no more rejects, but grants keep increasing because the movie is still being played. To prove that Wi-Fi can really harm Bluetooth and take control of the wireless channel in a selfish manner, we added to Ucode a few lines that check if a magic UDP killer packet is received. When that happens, the Ucode stops transmitting grant messages to Bluetooth. You see this happens at 2.6 seconds when there are no more messages in the green diagram. From there on, we cannot hear sound from headset, that means Bluetooth keeps being rejected. And we also found that if the forced pause is short, then audio restarts immediately when we transmit the magic UDP bring to life packet, otherwise Bluetooth needs to reconnect the headset. We tested this both on a Nexus 5 and on development boards from Cypress. This experiment clearly demonstrates that a denial of service attack from the Wi-Fi side against Bluetooth is really possible. Let's take a closer look now at the messages that Bluetooth sends to Wi-Fi and if we can use such information for an attack. These are the SECI time diagrams when we have a keyboard connected over Bluetooth. Depending on the keyboard, we can observe SECI messages transmitted every 15 or 30 milliseconds. Bluetooth sends these SECI messages to inform Wi-Fi that it is going to poll the keyboard, so that Wi-Fi defers channel access meanwhile. In this diagram, Wi-Fi is idle, so there are no reject messages from Wi-Fi. This is what happens when somebody is actually typing on the keyboard. At the bottom, we have the periodic sequence of SECI messages we saw before, one poll every 30 milliseconds. On top, we have the key presses sniffed by Wireshark when capturing from the Bluetooth interface. As we are typing with moderate speed, each key press is separate from the others, and we can also see the Bluetooth message with key release following each key press. In between, we can see the HID data captured by Wireshark with the specific event ID that represents a key press. Below, we see the SECI messages that we filtered on the Wi-Fi chipset by selecting the same message type. This demonstrates that at the Wi-Fi side, we can easily distinguish SECI messages related to key presses. So the bottom line is that this clearly demonstrates that having access to the Wi-Fi chipset is enough for measuring key press timings with very accurate resolution. And we know that in some cases, with the help of some artificial intelligence or classification technique, this is enough for guessing what a user is typing. We hence believe that without any further protection, the SECI interface can be used for mounting side-channel attacks, and we requested a CVE for reporting the associated vulnerability. So, Giska, the ground is yours again.
So, as Francesco has shown, it is possible to attack Bluetooth via Wi-Fi with some very simple coexistence mechanisms that might be present in many other coexistence protocols and just concern something like packet timing. However, there's one thing in the datasheet called WLAN RAM sharing, which we still didn't talk about. And I would call it the effect of when you spend too much time looking for side channels, like you dig everywhere, like here and there and there and there, but then you miss the one big thing, which is the WLAN RAM sharing. So it is actually here, so you can see like somewhere between Bluetooth and Wi-Fi, there is this connection, and there are actually two arrows for whatever reason, and they only go in one direction for another reason. And well, it's a bit weird, and there is nothing else written than this. So I was like, okay, I want to find it. Where is it? Where is this shared RAM? So where is it? Well, then I started looking in the Vice Studio, and the Vice Studio has like a few symbols for the Cypress boards that also include registers, and nothing called WLAN, Wi-Fi, whatever, also not in the coexistence registers, everything empty. But then in the studio, there's also one combo chip, which is actually in a MacBook Pro as well. And this one has slightly different symbols, so I didn't look into this one at first. And it has a couple of functions that are called WLAN buff something, sometimes with 1F, sometimes with 2F, so very consistent. And then there is one function that actually is writing some stuff into a register in an area starting here a bit higher, 680000, and then it's writing a word called Cafe Babe hex, and then afterward it reads and so on, like doing this in a certain manner. If you don't do it exactly this way, but just random, so to say, sometimes the Bluetooth crashes while doing this, but overall you can see some data. So I had like the impression I might be in as soon as I was seeing something called 802.11 something in the strings that I got from this area. But that was on a Samsung Galaxy S8, and then I was like, okay, can I get it working on more devices and so on? So I continued testing. So what you do is not just reading then, but obviously you start writing garbage. So this method once again proved very successful. And the best thing is that a couple of devices actually produce a Wi-Fi crash log. So when they crash, you would even get an image of the RAM. And this part even contains the shared RAM. And then you might be able to infer some packet pointers. And through those function pointers and stuff, and with the function pointers, you're actually able to set, for example, the program counter. So you can now write data, execute data, set a program counter and stuff like this. So you have, code execution. And this even on the Samsung Galaxy S10. And by the way, the newest Samsung Galaxy S20 has the same chip. So this should also work on them. Yeah, so finally, code execution within Wi-Fi via Bluetooth. And well, now you might say, okay, on which devices does it work? So here's a demo on the most recent MacBook Pro. You can see it's a one-liner. I just write this one branch instruction actually within code. So this time I'm not overwriting function pointer, but I really write code. And then you have a crash log that actually indicates that the program counter is there, and you can even see Wi-Fi restarting on top. And this video is in real time, so this is a super fast, super easy attack on the left-hand side on Bluetooth, on the right-hand side on Wi-Fi. That's it. So there is no separation. And the devices on that it works are really a lot. So initially I found the symbols on a MacBook Pro 2016. Sadly, I don't have that one with me, so I only have a ROM dump of it, so I couldn't test it, so that's why there is still the dot. Then there is the data sheet of the Nexus 5, which indicates that there is this sharing, even though I didn't find a shared RAM region on this one. So this is a bit weird as well. But I mean, maybe I just didn't find it and maybe it's still vulnerable, I don't know. But then on the newer devices, there's a thing. So this memory region, this 68 something that is within this WLAN buffer function is no longer referred. But still, you can write to it, and still you get code execution. And then there's the star on a couple of devices, because on some of them I was even able to observe kernel panics, and that's a weird thing. So let's say the next stage is the PCI exploit, and or it's called Express, but I think it's more like exploit because it really seems to be broken. And so when you write random stuff to that shared memory, what happens is that you get a lot of crashes. So this one is on another very recent MacBook Pro chip, and you can see like all the crash logs that I just generated by writing some garbage into the shared memory area and so on. Most of the time you would get into those in a certain amount of function that, for example, like this 16E093 one, because this is probably doing some memory check or something, and then this check fails. But then you might even get the program counter under control again. And then there are a lot of other funny, weird stuff, like failed to create a debug ring. This is, I think, during firmware initialization when something breaks there. and then even some kind of bit flip stuff all broken within this PCI Express communication probably. And so you might even get a bit more out of this. So I would call this like the most stupid fuzzer I ever wrote, because it is really not doing much. All it does is randomly writing stuff to a shared memory region. I don't get any coverage or something, but at least I get crashes. And then, well, not only Wi-Fi crashes, but actually kernel panics. And those kernel panics were like on the Samsung Galaxy S10e, but only if I had Android 9, and then also on the iPhone 8, on iOS 13, the iPhone 6 on iOS 12, and so on. Then even another macOS issue, but I think this one is just within the Bluetooth driver, so different one. And this is really fun. So here you can see it on an iPhone 6. The first thing that happens is, again, Wi-Fi disconnects, and then you would see again the reboot and so on. And definitely a different type of kernel panic. And this just proves how bad these drivers are even those days. So even after they have been exploited a couple of times, there are very simple bugs, very easy to reproduce with this method, that immediately kernel panic devices. So there is still room for improvement. So you might wonder how the world looks like for other chips, because probably other chips might be vulnerable as well. They also have coexistence interfaces and so on. And well, there is one trick as a reverse engineer, because as a reverse engineer, you would read specifications backwards, of course. And if you read the Bluetooth specification backwards, so you go to the very last page, which just, it only has the Bluetooth logo, and then the second last page. So this is the second last page, as you can see, you can check it out. And it's about the Wireless Coexistence Interface 2, which is MWS and so on. So the mobile wireless standards, which is coexistence with LTE. So this one is again just a very simple serial protocol for hardwired coexistence, as the stuff that Francesco was showing to you, but this time for LTE. Yeah. So there might be even more chips affected, and we even saw MWS being used on an iPhone. So they are very likely also attackable into the LTE direction. And well, I think almost everyone has proprietary coexistence features, and a couple of vendors also mentioned them briefly in their data sheets. So we asked Broadcom if we could also include other wireless manufacturers into the responsive disclosure process. And they said, yes, we can. So this is actually a very nice thing, because usually they were like, yeah, let's do this like slow and stuff and so on, right? But this time they were like, yes, include others, because others might be vulnerable, and that's very nice of them. And then a couple of manufacturers replied like, yeah, no, we are not vulnerable to this, because they don't even separate wireless cores. So the idea is they just have one core, and on that core they have like Wi-Fi, Bluetooth, or Bluetooth Zigbee, whatever, running at once. So you might say, yeah, by definition, you cannot escalate between those, because they are already equivalent in terms of code execution. But something that is still interesting are those operating system-based side channels. So when suddenly timings between Wi-Fi and Bluetooth both depend on the very same chip, and not just on some random collisions over the air, there might still be predictable stuff. There might still be stuff that you can influence from higher layers. So as a summary, what we achieved with the Spectra attacks so far is that if you have a Bluetooth RCE on a Broadcom chip, you can actually cause Wi-Fi driver kernel panics of different kinds. You can also get some information about the shared RAM, so you have information disclosure, and we have code execution. And in the opposite direction, if you have a Wi-Fi RCE, you can start attacking Bluetooth with denial of service, and also get information disclosure via key press timings. If you have further questions, there will be a Q&A afterwards, and of course you can also write emails to us or ask me on Twitter. Thanks for listening. Hi. So thanks for tuning in. I've already seen quite a lot of questions in the chat window, And what I want to add first is that I tested things again on the most recent iOS 13.6 and also Catalina 10.15.6, and it's still unpatched. So I guess it's like unfixable because it's very low in the hardware. The only thing that I fixed is that you can no longer send certain HCI commands to write RAM from the operating system into the chip, but this is something that you can bypass if you are root, and it doesn't like help anything against code execution. Then there's another question that might also be for Francesco, which is if we can explain a little bit more how the side channel measurement works from the Wi-Fi side of the chip.
Yeah, I see the question. And of course, if you already have access to the Bluetooth chip, you can read the information directly there. But the attack was thought differently. Basically, here we imagine that you have access to the Wi-Fi, but you don't have access to Bluetooth. And so you can use the information that are provided to Wi-Fi for inferring the timings that are actually only available to Bluetooth. So in this case, if you have this modified U code, which would be absolutely not detectable from the host, so you can monitor these Bluetooth timings, and you can actually transmit this information directly from the U code into a Wi-Fi frames without nobody understanding that you are doing this. So I hope this explains better the kind of attack we were thinking about.
Yeah, then there's another question, which is like if these attacks can be done remotely, and they need to be changed. So we have So we have Frankenstein, for example, to do some fuzzing and to find over-the-air remote code execution within Bluetooth, and then we can chain this. And so Frankenstein is something that we are going to present next week at Usenix if you want to see it. So this is kind of part 1 and part 2 of the research. And another question in the chat was if you have a different RF front end. So let's say if you have different RF front end for Wi-Fi and Bluetooth, if that prevents the attack. And now the issue is that a smartphone is like really, really small and it has nearby antennas. So even if you have like 2 antennas that are nearby, they interfere. And because of the interference, you actually have to make this. So if you don't want to have performance impact, you still have to do some packet-based decisions, and that is something that you would do over a serial line. So that means even between different vendors with different RF front ends, there are serial enhanced coexistence protocols just under different names and so on. And yeah, then someone asked like if the newest Android and so on would like help against those issues. And I don't think that you can do much from an operating system side. So it's like really something within the hardware, and that needs to be rebuilt in the hardware design. Yeah, so then there's question like how the collaboration with the hardware vendors was and stuff like this. So I mean, we talked to quite a lot of vendors, and some of them just said like we are not vulnerable because we already have a shared core. So for example, I think Qualcomm has like a combined core for Wi-Fi and Bluetooth. So they are kind of not vulnerable because the code execution is already there. So it depends a bit on the definition, and then other vendors just said like, yeah, we are like vulnerable to the line of service, but not to the code execution and so on. So it's something like you really need to build the POCs. The vendor would never say like, oh no, we are affected or something. So you really need to read the documentation, build the POC until they say, oh, we need to fix something, I guess. But I mean, at least they got the information quite a time before the talk, and so they have a chance to rebuild at least the newer chips. Now someone asked which kind of other devices are vulnerable. So I mean, everything that has like Bluetooth and Wi-Fi, it really depends. I mean, for Broadcom, I can say that like some smartwatches have it, but it's a bit random. I mean, nobody really writes which chips are in which devices. I think that Apple has like 25% of the chips that Broadcom sell or something go to Apple. But I mean, there are other vendors, other devices. It's hard to tell. Yeah, I don't really see any more questions. So thanks for listening. And there's also a longer Q&A session tomorrow at DEF CON. If you like come up with another question, you might also ask it there. Okay, thank you.
Thank you.